Hello everyone, welcome to this webinar series on MI2, Machine Intelligence on Modern Infrastructure. If you're attending this series for the first time, let me set the context. So MI2 webinar series focuses on the convergence of two independent but very interesting set of technologies, machine intelligence and modern infrastructure. Under machine intelligence, I cover a variety of topics including IoT, edge computing, artificial intelligence, neural networks, deep learning, cognitive computing, and so on. Under modern infrastructure, the webinars include Kubernetes, service mesh, ingress, gateway, and some of the upcoming microservices related technologies. Every alternate week, I switch between these two tracks, delivering one of the webinars from the machine intelligence or the modern infrastructure track. Every webinar is typically complemented by a tutorial that gets published at the news stack. And if there are code snippets that are shown, they become available on GitHub. And of course, the video gets uploaded to YouTube, which you can watch later. MI2 strives to be an independent and neutral platform to explore upcoming and emerging technologies. This is not driven by vendors or specific brands. The idea is to make sure that you get the exposure to some of the emerging technologies in the space of machine intelligence and modern infrastructure. So today, I'm very excited to bring you a topic on implementing real-time edge intelligence in industrial IoT. This is a very interesting, at the same time, relevant topic under the machine intelligence track. Let me introduce the speakers. I am Janaki Ram, Principal Analyst, Janaki Ram and Associates, based out of Hyderabad. I am a Google developer expert on cloud and IoT, Microsoft MVP for IoT, Intel software innovator for AI and IoT, and ambassador for Cloud Native Computing Foundation. Joining me is Sastry Maladi, CTO and co-founder of FogHorn Systems, and he is based out of Bay Area. So through this session, we want to introduce the concept of edge computing and what FogHorn calls as edgeification, followed by a couple of demos that I'm looking forward to share with you. So let me now turn it over to Sastry, where he will walk us through the platform that he has built, which is FogHorn. So Sastry, give me a minute while I make you the presenter.
Sure. Are you able to see my screen?
Yes, Sastry, we can.
Okay, let me just start the presentation slideshow here. Hopefully you can. Thanks everyone for joining this morning or evening, depending on where you are. Sastry Maladi. I'm going to give you a quick introduction about our company, what we do, and then delve deep into the technology and the offering. We are an edge AI, especially for industrial IoT company based in the Silicon Valley here. Been started about 4 or 5 years ago. All of these logos that you see on the left, those are all our investors. Because of the fact that we closely work with a lot of these industrial customers, we took investments from these industrial partners and technology partners. Many a times, in addition to us directly providing the technology to these customers, we also integrate our technology into these industrial partners offerings so that they can then further ship this to their customers. We have partners and customers across the globe. Many of them we have experience working with manufacturing, transportation, smart cities, buildings, and oil and gas. These are our top 4. Of course, we're also now cutting across telcos with both 5G and energy management. We get a lot of leadership awards. I won't bother you guys to go through all of that, but you will be able to see it later on when you get this recorded presentation. So what's the problem we're trying to solve? Typically, in an industrial environment, whether you're looking at an oil and gas manufacturing or transportation, any of these scenarios, the amount of data that's generated is humongous. Even if whether simple traditional sensors like temperature, pressure, velocity, and all of that, the amount of data every 30 seconds that a data packet gets generated. So you're talking about terabytes to petabytes of data. Simply sending all of that information into a cloud environment to process it is not practical for many reasons. I'll illustrate that in the next slide here. So when you have, for example, like an oil rig, or in this example, it could be a manufacturing machine too, that the data produced, if you wanted to send it to the cloud and process it there and then send the results back into that, it suffers from several problems. One is high cost. Yeah, first of all, there may or may not be any connectivity from these locations into the cloud. Even if there is a connectivity, the cost that associated with the bandwidth and the transporting all of the data to the cloud is cost prohibitive, right? It's quite high. Not to mention the latencies involved, plus the security risks associated. Many of our customers, many of these industrial players do not want to connect their systems directly into any kind of internet for the fear of cybersecurity attacks. So what we do instead is to provide an edge computing stack or a platform that can run either next to the asset, as you see in the picture there, or in some cases on the asset itself, if the asset has some compute capability, and then do the processing locally there. The processing includes both traditional analytics or machine learning and AI. We'll talk about the details as well as the demo that Janakram is going to do. And then only send the insights or the results into a cloud or a central data center environment. This actually addresses all of the issues we talked about, latency issues, cost issues, as well as connectivity issues. So the way the stack works is that you have all kinds of sensors that exist today, whether they're traditional sensors like temperature, pressure, velocity, flow, and all of that. Or these days, it's quite easy for people to install modern sensors like video camera or an acoustic sensor or a vibration sensor and so on. We take all of those live data sources in a streaming mode. There is no storage here because we're not storing all of that information or sending it anywhere else. And then we ingest it through this layer called data ingestion layer. The data ingestion layer supports ingesting it from many standard industrial protocols, OPC-UA, MQTT, Modbus, Zigbee, CAN bus, BACnet. Now we're doing Ethernet IP, a number of these different protocols that we're supporting based on the type of sensors and the devices. And then it goes through a series of processing layers in the data pipeline here. One is the data enrichment. Many a times the data coming in from these industrial sensors, the quality of the data is not as good. So you first needs to fix it. There could be missing values, there could be out of range values. Sometimes the data is binary in nature. How do you fix, cleanse, normalize, decode, all of that, and prepare the data into a format that is ready to be processed? And then that's followed by a CEP engine, complex event processing engine, that we built from ground up. This is a patented technology. And the CEP itself is not new. I'm sure most of you have heard about it. What's really novel here is the fact that you're running in a constrained environment. You're talking about typically running this in PLC or an asset or a ruggedized Raspberry Pi type of device or some other type of x86 based gateway. But generally speaking, small footprint compute, low CPU, low amount of memory, and almost no disk space involved there. How do you do event processing on the live streaming high throughput data coming in and be able to combine multiple types of data sources? This is what we call sensor fusion. How do you fuse different sensor types of data sources together? And that's followed by the machine learning. Many a times, customers may or may not be able to express, for example, what event or what pattern that they're trying to look for. Typically, if you know what pattern you're trying to look for, what event you're trying to look for, you can program that using our CEP. We have an expression language called VEL, stands for speed or velocity in Latin. That think of it as a combination of Python and SQL. Most of the data scientists folks actually like Python as a language. The syntax, we borrowed that syntax plus the SQL-like syntax for being able to work on streams, just like as if they were tables, but these are really streams. What machine learning brings is that if you're not able to express those patterns you're looking for, we can detect it for them, whether they're anomalies, whether they're regressions, or whether they are, especially in the vision-based system, if you're trying to do deep learning using neural nets and whatnot, failure condition detection, anomaly detection, or condition monitoring of the asset and things like that. And once we derive the insights in real time through a combination of these three layers, then we can publish those insights into a variety of destinations. They could be into a local historian if you prefer, or it could be any cloud-based storage. We have integrations with all major cloud providers, whether it's an Amazon S3 or Google IoT Core, or Microsoft Event Hub, IoT Hub, or even frankly traditional Hadoop, Kafka, types of systems too. But that is sending the results back into a central location, which can then later be used either for a site-wide visibility or for further fine-tuning of your machine learning models, which you can then push back to the edge. What we also have, which is not necessarily shown in the picture here, is a polyglot SDK. And using that, you can typically subscribe to these insights that are derived and then make a closed loop control action. For example, if you wanted to shut down the machine, if you want to send a control signal to the PLC to stop the machine or to activate it, you can do that as well. So in a nutshell, this is all happening at the edge environment in the industrial setting, close to where the data is produced, either next to the asset, or in some cases on the asset itself. The same thing was actually shown in an architectural diagram here in this picture. And the main benefits of this is the fact that this runs in a constrained edge compute environment, and we're cloud agnostic, we're multi-cloud, we work with all the different cloud providers. And the other thing that typically happens in the industrial setting is that these are not the typical IT people. Once you start talking about machine learning or CEP and all of that, sometimes it goes over their head because these are plant operators, engineers, and therefore we created operational centric environment, or what we call OT centric environment, tools that allow them to either drag and drop, for example, the sensor definitions, build the logic, and then be able to visualize them. A better version of an HMI. HMI is a human machine interface tools that typically people have. That's our core offering here. And of course, you have a Foghorn Manager tool that you see up the top there. That's typically run outside the edge device. And using that Foghorn Manager, you can manage and monitor hundreds and thousands of devices. Some of the industrial customers actually deploy 500,000 devices together and then be able to manage that using the Foghorn Manager environment. Now, I also wanted to illustrate one quick point on, in addition to the cost, security, and the latency benefits that I talked about for doing edge computing, even the accuracy of the models is actually a lot higher simply because we're working on a high fidelity data all the time. See this example of a customer signal here. We've got a suction pressure pump signal coming in. See, if you look at the raw data at the top, you see these blips coming in, circled with this red owls here. Now, when you send the same data to a cloud environment, typically you downsample. When you downsample by 30x or more, these signals look like how it is shown below there. You kind of miss the whole point. Basically, what we're saying is that not only do you avoid sending the cost of sending this and the latencies and all of that, but you get higher accurate results by executing your models directly on the high fidelity data. Now, here's the other concept, as Janakram briefly mentioned. We use this also a concept called edgeification. So normally when you go build a machine learning model in a cloud or a data center environment, you're not necessarily paying attention to the compute storage, the number of layers, the weights, and how much compute is needed. Mostly you've got elastic compute available. You can use as much compute as you want, but that's not the case when you in an edge environment, which is a constrained environment. So how do you take a cloud-based machine learning model that is developed to operate well in a cloud environment on batch data, to take that same model and run effectively on streaming data in a constrained environment? And that's really what we call edgeification, or edgeify the models. And the edgeification falls into two buckets. One is, of course, the hardware-based acceleration. If you happen to have in your device either a powerful CPU or an FPGA or a GPU, being able to detect those CPU category and be able to optimize them, whether it's Intel-based, for example, or whether it's an ARM-based, or whether it's a GPU like NVIDIA or other TPU-based. That's one part of it. And of course, not every edge device has such compute high-powered CPUs or TPUs or GPUs available. The other part we try to do is the software-based acceleration. So this is done typically by what we call quantization and binarization. As an example, normally when you do machine learning models, you're, let's say, operating on floating point numbers. You've got a 32-bit floating point number. And in a small constrained environment, especially because you're working on all of the high fidelity data, you may not need to work at that level. You can easily convert 30-bit floating point operations into like an 8-bit floating point operation. Or you can binarize those numbers instead of working across the data set that's coming in. There are different techniques that we use by applying those combination of this both hardware-based acceleration and software-based acceleration. You can see here I'm giving an example, which is in fact a deep learning neural net-based model built for one of the oil and gas customers, which is what we call the flare monitoring. On a video coming in, the model size, the amount of memory required to run the model, the processing frequency, as well as the size of the code is drastically reduced. In many cases, 10x or higher. That's how we're able to achieve being able to run these models in this small footprint environment. One other thing on the edgeification, remember I mentioned we have a CEP engine that is built to run in a very small footprint. Almost it just runs in few megabytes. The engine itself runs in few megabytes. And of course, how much memory you need for that depends on how much memory data points you're accumulating in memory at any given time. Because of the fact that that engine itself runs fast and it runs in a small footprint, in a machine, if you take an automated machine learning model, a lot of the times the most compute intensive part of the work is what is called a feature extraction or pre-processing on the data that's coming in before you pass it on to the machine learning model, which is, think of it as like an equation, right? So we extract all of the feature extraction capabilities and pre-processing and as well as post-processing into the CEP engine itself to offload the compute requirement on the machine learning engine itself. So these are all the techniques we used that made it possible to run the same models at a higher speed and accuracy. The other thing we do, typically what also happens in the industrial environment, just like everything else in life, that even when you go build a machine learning model, train it, and then deploy this model onto an edge environment, and it starts detecting or predicting these results accurately, what happens over time is there could be changes. For example, calibration issues on the sensors. Previously, if a temperature sensor was sending the values from 0 to 100, it might now be sending from maybe -1 to 99. It just that because the values have changed, your same machine learning model that once accurately used to predict the results may think that there is an issue there, may no longer be able to accurately predict the results, right? And there could be other reasons too, environmental conditions, external conditions, machine behavior changes, and all of that. So what we have built is a module as part of this EdgeML, which is our machine learning engine, inferencing engine here, to start detecting the degradation in the level of accuracy of these predictions to a variety of mechanisms, whether through F1 score, whether it's through clustering, and a number of other things too. And once we detect there is a degradation, we automatically enable a data publisher to start sending the raw data around that time period into a retraining module. We've actually done the initial integrations with Google cloud-based retraining tools. Now we did that with Azure. We'll be doing the same soon with AWS too. But the key here is the fact that we can detect the degradation when the accuracy of the results go down, automatically retrain the model, and then pull the model through Foghorn Manager back onto the edge environment and deploy this, and keep doing this iteratively until the accuracy of the model comes back up to what it once was, right? This is what we call closed-loop ML or edge AI, artificial intelligence, in the sense that this is a self-healing, self-correcting machine learning model execution on the edge, so that it can continue to predict the failure conditions. Whether, when I say failure condition could be a machine going down, or a part that's being manufactured by the machine is defective, or whatever the case might be. And this is actually quite powerful. Many of the manufacturing and oil and gas customers have deployed this kind of an environment to continuously predict the correct results. Traditionally, initially, we have released all of these capabilities on as a set of Docker containers. For example, we release this as containers, and customers can also customize individual capabilities. For example, if somebody doesn't want a Modbus because they don't have a Modbus device, or if someone doesn't want a local historian because they don't have disk space, all of that can be customized. It's quite flexible. And then the beginning of this year, we've also released the same capability. In fact, the industry's first capability to release on a Android-based handheld device. Initially, Honeywell was actually using this. They're shipping it now. We have a number of other customers, pretty much fleet management companies and other companies, and even oil and gas companies, where operators can move around with the device in their hand and then predict a lot of these things by simply pointing at the flare and things like that. So it's same architecture as what I described before. The slight differences between the Android version versus the non-Android version here, because in Android typically you don't have, people may not use these industrial protocols. You have these Android events, you have your shared memory based, you have a local historian is mostly SQLite and things like that. So it's the communication and infrastructure mechanism is slightly different, but the CEP engine and the machine learning engine, of course, and Android is based on the Java-based thing. So the machine learning engine takes the Java-based models there. And of course, all of the TensorFlow Lite and number of those libraries are already available on Android too. So we provide the same capability on Android. We do have a huge ecosystem. As they say, it really takes a village to get the whole end-to-end IoT solution in place. We provide the core capability for being able to configure the sensors, sometimes auto discover these sensors, configure these analytics through CEP well expressions, and the machine learning models and derive these insights. Of course, we have partnerships with all the industrial providers. That's where they get the domain knowledge from. When somebody says, I've got a CNC machine not working, when somebody says, I've got a tree turbine or a wind turbine or an oil rig, those industrial customers actually provide us and bring us the domain expertise. Of course, we have built that over time now. All the cloud providers, we're not competing with the cloud guys. We're complementary to cloud. We collaborate and work with them. And all of the hardware supplies, of course, we test. Even though we ship all of the containers, both for one for x86, one for ARM-based, we still pre-test on a number of these devices. Some of them are listed on the bottom left here. And then, of course, a lot of SIs too. How do we take this to scale? We can show, for example, predictive maintenance of a machine failure and all of that. But when somebody wanted to take this and deploy this across hundreds of factories or things like that, they can engage an SI who can help them go deploy this too. And we also closely work with all the chip manufacturers. And Intel, of course, is an investor. We closely work with Intel, ARM, Qualcomm, a number of those guys, where we're continuously trying to figure out whether we can leverage the optimized chip instruction set to run this better and faster. Implementation of our software itself, of course, is all done in C++. We natively compile them to leverage the platform capabilities. That's in a nutshell the generic platform. The offering itself is generic. Customers can deploy that platform using our tools. They can solve any specific set of use cases, whether we're talking about, as I said, manufacturing, transportation, and whatnot. What I want to talk about is just a couple of use cases. We've got hundreds of use cases we experience working with. And maybe I'll talk about just briefly a couple of customer use cases and turn it over to Janikaram, who will actually do a live demo here. This use case I'm talking about, it's a manufacturing plant. In fact, it's a GE manufacturing plant. That plant manufactures these industrial grade capacitors, as shown in the picture on the left. And the manufacturing process for the capacitor itself involves 3 different stages. One they call the winding phase, which is really they take an aluminum foil and then using a Kohlmorgen winding machine, they wind those coils and press them into packs. You see on the left those white grayed out silver packs there. And then the second step is to run it through what is called a treat oven, which is to take out all of the moisture from the capacitor, subject it to heat and pressure conditions. And finally, they fill different types of oil into the capacitor and then to test it. At this point, their challenge was when they sealed the capacitor and tested, a lot of them were seeing dielectric failures, right? When that becomes a scrap. So this was costing them millions of dollars because there's a lot of scrap. There's really, unfortunately, they couldn't do anything. It's beyond a certain point. So what we did is we, for example, this capability or the technology that I described, we installed it on a little gateway like a Raspberry Pi, connected to all of the sensors from the winding machine because the customer wasn't sure whether the failures were occurring during the winding phase, treat oven phase, or the last phase. What we actually shown them is that the failure were actually caused at the very first stage itself. Using this analytics and machine learning at the edge, we showed that even a small difference in the tension, width, or aspect ratio of the coil was causing the dielectric failures when you fill the oil between them. So this is how they were able to almost eliminate all of their scrap and improve their yield. Same concept we applied to many manufacturing use cases as well. The second one that I want to briefly talk about was, which actually was in oil and gas, but you can apply the same concept Typically in a gas refinery, this was one of the largest plants in Saudi Arabia and the kingdom. Aramco is an investor as well as a customer. So what happens is when you're refining and processing gas, due to many number of reasons, whether there's a foaming issue, foaming is a concept of converting all of the sour gases into sweet gases. In the process, there could be some issues and foaming could happen. Or there could be a compressor issue, the compressor which is actually refining this, it could go bad, or it could be other reasons too. So regardless of the failure conditions or the reasons, when that happens, typically what they do is they release the gas through what are called oil stacks, somewhat similar to the picture that you see in the left there. And when they release the gas gets burnt and you see what is called a flare there, which in itself is bad. But what happens sometimes is also that flare turns into smoke, a dark smoke, which actually is indicative of other problems further up in the stream, which is worse. So this has both a business problem because the customer, for example, is releasing this gas and losing the value. Second, it also has environmental issues too. The World Bank, for example, very closely monitors using EPA regulations on who is emitting these toxic gases into this atmosphere. And so they get closely monitored, and if somebody is actually releasing them, they get penalized. So what the customer wanted to do is to be able to proactively predict and be able to identify when there is in fact a flare, certain characteristics of the flare, what's the size of the flare versus the size of the smoke that's coming in, what's the relative percentage, as well as what's the volume of the gas that's being released. That actually directly correlates to their business, quantifying their business value, as well as the composition. Sometimes they actually, for the EPA regulation reasons, they need to know, is it ethane, methane, butane? Well, what's the composition of the gas that would actually releasing into that? How do you do that? So they've installed video cameras, and then in a control system attached right next to the stack, we put our software in there, and we feed that video along with other compressor information, and then using a neural net based model and the CP well analytics, we exactly identify in real time the characteristics that they're interested in and alert the operator, so the operator takes appropriate action. Again, we've extended this use case, video-based, video, audio, acoustic-based use cases into manufacturing. We do elevator controller manufacturing. We deploy this across millions of elevators running on top in a control system. We could also do high speed in a tape measurement scenario in a manufacturing, security, facial recognition. We're also into transportation, which is we started with a locomotive. For example, the picture that you see there, the locomotive already has a built-in engine. They wanted to use case to optimize the fuel efficiency and the consumption for that, right? But there's no additional computing capability you can install. So we put our software inside the engine compute itself. They gave us part of a line card. Because of the fact that we can run in a small footprint, we were able to run the software there, connect the sensors that are coming in, both, and then combine it with the external GPS location thing. Because one of the things they wanted to know was if the train was, engine is running, it is close to where it is supposed to reach, but it's currently idling and has not reached there, that is burning a lot of fuel too. In order to find that condition, you also need to combine the fuel information with the external GPS location information. We did that. That's the sensor fusion thing that I was talking about. Subsequently, we also did, now in fact, you can find that out and Google up on this as well. We are now into the Porsche cars, for example. We're doing a multi-factor authentication. In the Porsche cars, normally these days when you have cars, we have this keyless entry. Most of the time, as long as you are standing nearby, somebody else can open the door, right? So how do you protect from a security standpoint that the real owner of the car actually can open the door? So what we did is we installed a camera in the rear view mirror of the car, and then pointed using the facial recognition of the person walking in, be able to identify if that person is the owner of the car. But obviously people are getting smarter, right? So if I happen to know who is the owner of the car, I can print the picture of that person, put it on my face and pretend as if it's me, right? So to prevent that, we then installed an IR camera, which is a heat sensing camera on the other side of the rear view, and then combine these two to identify if it's a real person plus he's the owner, and then use a third factor to associate with using Bluetooth, whether to the cell phone that the owner actually owns. When all these three conditions match, then we automatically open the door. This was a use case with the Porsche. You can actually, Porsche themselves blocked on this thing we can talk about. Now what we're working on is actually running in the ECU of the car itself. For example, cruise control, or if there is obstacles coming up on the road out there, how do you automate the pedal pressing and the acceleration based on what's happening around it, not just simply based on the speed set by the user. So we're building a machine learning model to run inside the ECU. That's going to be coming out soon as well. So very, very interesting use cases. We started with locomotives into now autonomous driving vehicles in the passengers cars. We've got a lot of fleet use cases as well. I think in summary, what I want to say is that the use cases are vary quite a bit based on the industry and the specific use case. What we built or providing is a innovative edge AI technology that can run in a very small footprint compute environment, can work with existing compute, or it could be both greenfield, where you can run it in a separate gateway attached to the asset too. And we work and support all of the industrial protocols to be able to do that. That's the technology part of it. Now I would pass on back to Janikram for you to show a demo of this technology, how it works. Let me make you a presenter again here.
I'm already a presenter. I took over the control.
Oh, you did? Yeah, great. Okay.
Okay. Thanks, Sastry. That was a pretty exciting technology and a platform that you have built. So a quick disclaimer, I work closely with Sastry and rest of the team as a consultant and as an analyst. I have had experience using the platform for a while, and having worked with multiple other edge computing solutions and edge computing POCs, I think Foghorn has a unique standing in the market. They are the first multi-cloud and edgeification platform that stays close to the device. There are multiple platforms, but Foghorn is very unique in a way that it is actually very cloud agnostic, very protocol agnostic and language agnostic. It can be deployed in a variety of environments and talk to a variety of cloud platforms. So with that disclaimer, let me set the stage for the demo that I'm going to walk you through. So I have two demos. The first one is more like the context setting and introducing the platform. And the second one is slightly advanced scenario where we actually roll out a machine learning model to perform predictive maintenance. So let me give you a visual representation of the first demo. So think of a smart building scenario. So in a smart building, there are multiple floors, and it's a skyscraper. So there are multiple floors, and every floor has a dedicated HVAC, which is the cooling system. And there is a centralized command and control center to basically monitor the efficiency of each of those HVACs. So basically, the idea is for every floor of the smart building, there has to be a visual indicator that tells whether the HVAC is functioning the right way, whether the optimal temperature is being maintained or not. And the dashboard shows a color-coded heat map like visual indicator telling which floor of the building is optimal or is not meeting the threshold, which is hot, which means it also impacts the power efficiency. So basically, we will set up a dashboard that actually shows a visual representation of the optimal HVAC performance. So that is the scenario, a smart building with multiple floors, and every floor having a HVAC, and there is a command and control center to basically monitor the HVAC performance for each of the floors. So the building already has an existing MQTT broker. So an MQTT broker is a message bus a platform that enables pub-sub functionality between sensors and actuators. So the HVAC is connected to a set of environment sensors that predicts or that actually publishes the data of temperature, humidity, and so on into the MQTT broker. And then the dashboard that is actually showing a colored LED is also published, is also subscribed to the same MQTT broker, but to a different topic. Now, the objective that the customer has is to basically create a very dynamic analytics-based rule to make sure that they are able to change the color of the bulb with a predefined threshold. So based on how the humidity is changing, they want to publish the data to the MQTT broker so that the subscriber, which is the bulb running in the command and control center, automatically changes the color. So there are two edge devices, one edge device connected to the HVAC which has an environment sensor. The other edge device is connected to a set of LEDs that glow based on the threshold that is currently being met. Now, this MQTT broker, which is already deployed, is integrated with FogHorn Lightning platform, and we use the CEP that Sastry talked about, which is actually using a domain-specific language called WHAL. So using WHAL, we implement a very simple rule. We can go far beyond that, but I want to show you how to create and configure a simple rule that takes the input from the environment sensor coming via the MQTT topic, modifies and transforms that stream and republishes it back to an existing MQTT broker so that the bulb changes its color. Now, the idea of this demo scenario is how can Foghorn get integrated with an existing message broker seamlessly without really disrupting anything or without rocking the boat. So the smart building already has a few edge devices. It already has an MQTT broker, and now we will integrate this configuration with FogHorn Lightning and extend the functionality by writing a simple WHAL expression. So there are a couple of steps that we need to perform before we can start implementing this. So there are actually 5 steps. So we need to register the MQTT server that is already running in the customer environment. So for the entire building, there is one MQTT server. So we will start by onboarding that MQTT server into FogHorn platform. Then we'll create what is called as an edge solution. So an edge solution is like a logical boundary. It's a deployment unit that impacts one edge device at a time. So we will actually create an edge solution that typically goes to the environment sensor connected to the HVAC. And then this edge device that we are registering has few sensors. For example, there is a temperature sensor, there is a humidity sensor. Now we need to onboard those leaf devices, which are actually sensors, into Foghorn, which is the 3rd step. Now, once we have all the devices, that is both the edge computing devices and the sensors onboarded, we go ahead and create a WHAL expression, which is going to be the rules engine, which will route the inbound MQTT, modifies that, and then it routes it to another MQTT topic, just like a simple rules engine. And finally, we go ahead and deploy this entire solution to one of the edge devices. So with that, let me switch over to the demo. So let me show you the interface. So what you see here is the Foghorn Manager. And think of Foghorn Manager as the control plane. Now this runs away from the edge devices. For example, for the entire smart city setup, there could be one Foghorn Manager which will register all the smart buildings and along with all the edge devices and the sensors into one environment. So that is the control plane, that is the Foghorn Manager. Now remember, the first step was to basically onboard the entire configuration. So here you notice that I have 2 devices that are edge devices. As a part of the installation, I have gone ahead and onboarded these devices. So Pi1 is actually a live device that is running next to me. Unfortunately, I don't have a camera to show you those devices, but it is running on a Raspberry Pi with a specific IP address, and this is already registered. Now, Pi2 is also another edge device, and it is connected to the command and control center's visual indicator. Pi1 is connected to a HVAC that is streaming the environment sensor data. So with these 2 devices in place, it's time for me to onboard the MQTT broker, which is the very first step. So to save time, I have already gone ahead and registered this, but I want to walk you through the steps involved. Now, adding a new server is pretty straightforward. What if the devices are talking to not an MQTT endpoint, but an OPC UA server? So you can also onboard that. And if your environment is already connected to some of the cloud-based IoT platforms like Google Cloud IoT Core, Azure IoT Hub, or even a Kafka endpoint or a traditional Modbus, you could bring all of them into the fold of Foghorn Manager, and any sensor data that is flowing back and forth now it will become visible and will become available within the context of Foghorn. So that is the advantage of registering a server. So when I choose MQTT as the server, I can give a name, something like building 1, and then give the name or the DNS name or the IP address. and then just register that. Now, as soon as we onboard this, it shows up here. If you have other servers like Azure IoT Hub or Google IoT Core, you could onboard all of them here, and they show up in this section. So that is the first step. Now we have seamlessly integrated an existing MQTT broker from the customer environment into Foghorn Manager. So once we have that, the next step is to basically onboard the sensors. So before we could onboard the sensors, we need to create what is actually called as a solution. So a solution is like a logical group, as I mentioned earlier. Let's call this building one. Now, building one solution is like a resource group. So this is going to be the logical boundary for all the sensors, all the Foghorn specific configuration associated with that specific edge device. So we will choose building one's HVAC, and then I click on deploy just to make sure that it is actually hitting the edge device. And once that is selected and deployed, I go to sensors. Remember, HVAC has two sensors. The edge device connected to the HVAC has two sensors. One is an environment sensor, which is nothing but the temperature and humidity one. And it also has another sensor, which is actually coming from a different room or a different floor. But for all practical purposes, it's also a sensor that is associated with this. So we'll also onboard that. And it is actually a bulb. It is not a sensor, but an actuator. So we'll go ahead and add that as well. So now I'm going to call this as ENV, which is the environment sensor. And then the source topic, where exactly is the topic getting published. And this is from the existing MQTT server. So we choose building one MQTT server, and let's call this demo/env. That is the standard MQTT topic to which the data is getting published. Now what I'll do is I'll actually switch to my live environment. So if you look at this, I am currently logged on to one of the Raspberry Pis, and what I'll do is I'll start ingesting the data. So this is sending the HVAC data straight into my MQTT broker, and from MQTT broker to Foghorn. So the reason why I copied this is to create the schema. So what I'll do is I'll choose custom and then generate schema from sample data. I paste this inbound JSON payload and click on generate. And then Foghorn will go ahead, parses it, and then it basically generates the schema expected from this stream. So we will now save this, and the environment sensor is registered. Because both the bulb and the environment sensors are connected to the same MQTT topic, I technically register the other one as well. So let me register the bulb edge device, which is coming from the dashboard. So this is actually coming into demo/status. So that is the topic to which I'm going to subscribe to. And then data type is string because we are sending the color, which is red, green, or yellow. So I'll choose data type as string and register this sensor as well. So now we have two edge devices, two sensors that are connected, and one MQTT broker. Perfect. So let me hit deploy so that it actually gets applied to the edge device. And now once we have this in place, where we have the sensors already connected, I'll switch to what is called as the MQTT Explorer. And here you notice that demo/env, this data is already flowing. So if you look at this, the MQTT broker is already receiving the data. The count is increasing and the temperature and humidity data is changing. So this is nothing to do with Foghorn, but it is just an MQTT Explorer that is showing us the status. So now what I'll do is I will, on the subscriber, on the dashboard, I go ahead and execute the Python code that is receiving the inbound stream, which is basically controlling the color of the bulb. Now, to one of my Raspberry Pis, I connected an LED matrix. It's actually showing the color in the live environment, but I don't have a camera, so I cannot show you. But as soon as we connect the dots between the inbound MQTT stream and the outbound MQTT stream through the well expression, this will start receiving the subscription. So let me switch back to Foghorn Manager and go to analytics. So here, this is the complex event processing engine that Sastry was mentioning, and it comes with its own language, which is a combination of Python and C, or Python and SQL, more or less, and it is a domain-specific language. So you could use an IDE to visually build it, but since we are using a very simple expression, I will use the built-in editor. So I'm going to call this the color, right? Just a color, because what we are doing is we are taking the inbound stream and adding a color to it so that the bulb can change its status. So I'll call this expression color. And where is the input coming from? It is actually coming from the environment inbound stream, which is again an MQTT topic. This internally associates the inbound MQTT stream with the Whale rules engine. And in the next step, we can basically use a few lines of Whale expression to control this. Now, let me show this in a bigger screen. So this is the domain-specific language, DSL, that Whale uses. So we are defining a stream called environment, which is actually coming from the MQTT topic, and it has humidity as integer, count as integer, humidity and temperature as real. It matches the schema that the sensor is sending. And here I write a simple switch case statement where I'm saying if the threshold is more than 46 and less than 55, which is very hot or very humid, make the bulb red. If it is between the range of 15 and 25, make it yellow, and anything less, always run it as a green. So I put this as a condition, and then I define another outbound stream called bulb color. And here I am introducing a new value into the payload, color as color indicator, and this is coming from the function that we have written here, the expression that we have written. So color is color indicator, and then we are using data.humidity as it is, which is the input parameter for this. So this gets replaced with H, and that's how we are evaluating the expression. And then remaining elements remain the same. Count, humidity, temperature remain the same. So we are grabbing the inbound data from environment, appending a new element to the JSON payload called color by applying this rule, and generating a new stream called bulb color. So now I will click on next, and you can see that the input for Whale expression is coming from the MQTT topic. The outbound stream is native to Whale and Foghorn, which is called the analytics bulb color. Now, if you're actually wondering what is analytics/bulb color, it is an internal stream that Whale is publishing. It is still not bound to an external MQTT topic. So that's our next step. But before I go any further, let me go ahead and deploy this. So at this point, the expression is pushed to the edge device. It could be multiple edge devices if they are all registered as one unit. And then I go to data publications, and here I need to perform just one step, that is taking the local message bus topic, which is the output from the Whale expression and the CEP, and actually publish it to the outbound topic, which is the MQTT topic. So let's call this as env pub, and then I'll choose the server type as MQTT, select the building one MQTT server, destination topic is demo/status. That is where my actual dashboard is subscribed to. And then we'll say, take this message bus topic, and then associate that with the MQTT topic, which is demo/status. So by now, you could easily sense that we are dealing with two different message buses. One is the external MQTT broker that is enabling the communication between the sensors and actuators. Then there is another message bus that is very internal to Foghorn, which is used by the pipeline components managed by Foghorn, and CEP is one of the components of that pipeline. So that pipeline is publishing to this topic called analytics/bulb color. Now we are associating the internal CEP pipeline based topic to the external MQTT topic. Now I click on save and click on deploy. Now in just a few seconds, we should start some output on the other Raspberry Pi. There we go. Now you actually see that the color is getting appended and it is yellow. So now what we'll do is I will keep both the windows open. So now what we'll do is, just to see this in action, I come back to analytics, I modify my threshold, right? So here I'm actually saying that if the threshold is between 15 and 25, make the color yellow. But by increasing the range, for example, my humidity currently is reporting to be 22.35 or 23. So what I'll do is I'll actually say, turn this into yellow only when the humidity is more than 25 and less than 35. So, or less than 45, so that it actually meets the above condition. So now we are actually increasing the threshold. I click on next. I will finish this entire thing, and now I click on deploy. Now as soon as I hit deploy, this entire configuration gets pushed to the edge device, and you will notice that immediately right after I hit the deploy button, the color changed from yellow to green. And in fact, in my live environment, I can see the LED matrix turn from yellow to green. Now this is the power of using a complex event processing engine in real time without disrupting your existing setup. Mind you, we haven't meddled with the code. We haven't meddled with the existing MQTT broker. We brought in Foghorn Manager as a control plane, which has seamlessly been integrated with an existing MQTT broker, and it has taken over the entire control without really changing any configuration. Now, let me show you what went behind the scenes. So this is my publisher. So this is currently running on one of my Raspberry Pi devices. I'm using PAHO MQTT client, and I'm using a sensor called SenseHat. And what it does is, it basically grabs the sensor data from the SenseHat, and I'm only taking the humidity and temperature. It actually streams a variety of parameters, but I'm only interested in humidity and temperature. And I'm turning that into a JSON payload and publishing that to demo/env topic, which is based on my MQTT broker listening at this IP address. So this is how the HVAC is publishing the data to the MQTT broker. And the dashboard, which is actually showing the heat map in a color-coded display, is exactly the same code, but here we are actually subscribing. So we are subscribing to a topic called demo/status, and demo.status, as soon as there is an inbound message, we go ahead and we deserialize the payload from JSON to the local Python list, and then I apply a simple if-then condition to turn the actual color into an RGB code. So which will basically change the color of my bulb. Pretty straightforward. Now this code doesn't need to know that it is running in the context of Foghorn. That's the beauty of our existing demo. So that was the first demo. Now
one quick comment, if I may make, Janakram, is that to the audience, is that the well expression how Janakram showed, that's the one way to do it. In an OT environment, if the operator wanted to use a graphical interface, they could also do it without actually having to write the code. Just wanted to pass that comment. Yeah.
Absolutely. So you could also use the IDE or the built-in graphical editor to basically create this expression. Thanks, Asri. Yeah. So that was the first demo, where we went through the workflow of onboarding an existing MQTT broker, onboarding the edge devices, the associated sensors, and creating an entire pipeline. The next demo that I want to show you is a predictive maintenance demo. And for that, I'll actually switch to another environment, another directory, and so here, if you actually notice, I have some Python code and there is a data set. So basically, this is the historical data set of a turbine that is generating data related to rotation, which is the RPM, the temperature, vibration in hertz, temperature in decibels, temperature in Fahrenheit, sound in decibels, and the output value represents whether there is a defect or an anomaly in the stream. So this is my training data, which has been collected historically by running it in the live environment. And now I actually want to use this training data to create a predictive maintenance model and run it at the edge, not in the cloud, not in the control plane, but very close to where the actual turbine is. And then the Python code that you see here is a turbine simulator. So here it's again publishing to the same MQTT broker that's registered with FHM, Foghorn Manager. And then it simply publishes some data with a flag whether there is an anomaly or not. Now, currently, I put the fault flag to false, which means there is no anomaly. It publishes within the acceptable range that I have defined. Nothing scientific. This is just based on some gut feel that the rotation should be between 200 and 400, temperature should be between 47 and 72. So we are just simulating the entire data here, and then we generate a payload which closely mimics a NumPy array. More on that a little later. And this is going to be pumping in the data straight from the turbine into MQTT broker and from there to FHM. So now our goal is to implement a predictive maintenance solution. So I have already gone ahead and created a solution called Turbine. This turbine is responsible for onboarding the turbine data as well as the actual EdgeML. So here is the EdgeML. You can add an existing Python model that is a pickle file or a .py or a joblib file, or you could also train a new model. So let's call this turbine defect. So this is a model that we are creating right on the device. So all the classic ML models and on the algorithms like linear regression, logistic regression, SVM, ADA boost regressor, decision trees, KNN classifier, all of those are available here, which means you don't need to really write Python code to implement that. This is out of the box. This is running right at the edge, not on a GPU or not away from the devices. So we choose logistic regression because we want to generate a 0 or 1, and it comes with some set of hyperparameters which we need not touch. These are the optimized parameters. Then I choose next, and here it basically asks me for the historical data set. So I browse and I pick up the dataset.csv that is already containing the historical data. Click on next, and here I choose the topic, which is the MQTT Turbine, and that is being published to message topic. And then the output is actually published at turbine defect. So now we leave this as it is, click on next. And if you notice, the input to the model is coming from the MQTT topic in a decoded form, and the output is published to turbine defect. Now I click on finish. I go ahead and deploy this to my edge. And in a few seconds, you see running, and that is extremely fast. So now the model is listening for inbound messages. And what I'll do is I'll actually go ahead and start ingesting the data by running my Python, turbine. Okay, so Python turbine.py. So this is going to send some data representing the turbine simulator. So now I can go back to data publications, add a publication, put it back to MQTT and take over from there. But I want to show you a very simple visualization. So basically, Foghorn comes with a set of pre-built applications, and Viz, which stands for visualization, is one of them. And it is already running on the edge device. I have gone ahead and deployed because it takes a few minutes to pull the images and configure. So this is already running. So I click on this, and this is basically the dashboard. So here, let's pick up a text card. So, or actually a bar chart. So here we will call this turbine defect, choose a topic, and the ML turbine defect is the topic, and we'll call this as time, and then the y-axis as defect. So currently, if you notice, it is 0, which means it is not predicting any fault. Now let's keep this dashboard running, and I will close this program. And what I'll do is I will force an anomaly by turning the fault to true. Okay, so now I'm going to ingest the data all over again, this time with a fault, and immediately you actually see that it is hitting 1. And this indicates that it is predicting a fault because there is an anomaly in one of the data points. So if we switch back, okay, and run it all over again, it goes back to 0. And that is an indication that the model is working and it is basically predicting when this turbine is going to fail. So it can't get simpler than this. Beyond using the inbuilt algorithm, you could actually bring one of the sophisticated models written in TensorFlow or even OpenVINO models that are optimized for Intel Movidius and MyriadX VPUs. There is no limit. You could technically bring any sophisticated neural network and run it as a part of EdgeML. As Sastry mentioned, you could also create what is called as closed loop, which will detect a drift and automatically trigger the pipeline responsible for retraining and deploying the model. So this is just the beginning. This is just scratching the surface. So that brings us to the end of the demo. And just to summarize, these are the steps that we have gone through. We registered an existing MQTT server running in the smart building scenario. We created a solution, which is the logical boundary. We onboarded the sensors, the HVAC environment sensor and the bulb. And then we created a well expression and routed the new MQTT payload via the expression. And we have deployed it to the edge. And for the predictive maintenance, most of the steps remain the same. We actually created an EdgeML artifact and pushed it to the edge to perform predictive maintenance. So that brings us to the end of this. Unfortunately, we are almost out of time, so we are not able to take questions, but you have my coordinates. You can always reach out to me and I'll forward it to Sastry or the team at FogHorn. I want to thank our sponsors, Google Cloud, the premium sponsor, who has been supporting me with all the logistics and the credits to develop these demos. NewStack, my media partner, where all the articles are published and tutorials show up. Foghorn, I'm honored to have Foghorn as both my client as well as my sponsor. Portworx, another Bay Area-based company, again, my client as well as a sponsor for the MI2 webinars. So that brings us to the end, and most likely this is going to be the last session of this year. I'm going to do a little bit of rebranding and relaunch MI2 in January 2020. So I'll see you at the other side of the year when we are ready to refresh and relaunch MI2 after a break in December. And I want to take the opportunity of thanking Sastry. He has been kind enough to join me as a co-speaker and walk us through Foghorn. And I really enjoy working with him and the rest of the team. So stay tuned for my upcoming series. I'm going to send out a communication to all of you on the calendar for Q1 2020. Have a great holiday season, and I'll see you in the new year. Thank you.
Thank you, Janakram. Thank you all for attending. And as the Janakram said, feel free to please reach out for any additional questions you may have.